All right. So we've got a map here, a mapping. We've got states and their population. With your neighbor, decide, name a state that has a population of 8.3 million. Talk with your neighbor for a second. Name a state that has 8.3 million. Ready? On the count of three, you're going to say it. 1, 2, 3. Good. It's North Carolina. Very proud of you. Good. Next one. We're going to name one animal that has a life expectancy of 10 years. Name one animal that has a life expectancy of 10 years. Talk with your neighbor. Ready? I'm going to count to three and then we're going to say it. Ready? Life expectancy of 10 years. 1, 2, 3. See how everyone said something different because there were multiple options. We had a duck, a lion, or a pig who had a life expectancy of 10. Okay. Is this first equation a function? Or first relation? Yeah, that's a function. Okay. Is the second relation a function? Disagree. Is this second relation a function? Yes. It would not be a function if a cat could live 11 years and 10 years. Okay, if that was the life expectancy. Remember, it's when the x goes to two different y's when it's not a relation. It is a relation. This is a special kind of relation. This is called it's a function. Sorry, it is a function. It is a special kind of function. This one is called a 1-to-1 function. It's 1-to-1 because each x value goes to one y value. Each one goes to 1. Okay, let's look at this for a second. Trying to decide if this thing is 1-to-1. Looking at this first mapping, do you think this mapping right here is 1-to-1? No, because I've got 2 going to the same one, so this is a no. Look at number 2. Is number 2, this relation right here, is that 1-to-1? Let's look at the x values. I got 5, -2, 6, 0, 2. Do any of those repeat? No, so we're good. So let's check the y's. 1, 7, -1, 4, -8. Do any of those repeat? Nah, we're good. The x's all happen one time. The y's all happen one time. Then that function is considered 1-to-1. What about this graph? Do we think this graph is 1-to-1? This graph is not 1-to-1. Anybody have an explanation as to why this graph is not 1-to-1? It passes what? It passes x equals 0 multiple times. This x is equal to 0. Right here, x is equal to 0. Right here, x is equal to 0. So it is not going to be 1-to-1. Okay, let's try a couple more of those. Let's look at these graphs down below. What do you think on graph number 1? Do you think graph number 1 is 1-to-1? No, because I touched this dot and that dot. X is equal to like 1.5 and also right there. We're repeating x values. What about number 2? That one is 1-to-1. Number 3, that is 1-to-1. Come up with a way of telling as you look at a graph whether it is 1-to-1 or not. Talk with your neighbor for a second. A graph is considered 1-to-1 if what is true? Aaron, what do you think here? How can we tell if it's 1-to-1? A horizontal line test. We did a vertical line test to decide if the x is repeated. To see if the y is repeated, it also has to pass the horizontal line test. So if I drew a horizontal line test, it failed. Horizontal line test, we're good. Okay, that graph is strictly increasing, meaning it's only going up. That's 1-to-1. Okay, the only other type of graph would be a strictly decreasing graph. It's going to pass the horizontal line test as well. Horizontal line test, we're passing it. Okay, that is how we determine if something is 1-to-1. So let's go to notes. A lot to get through today. We'll go at nothing super crazy, just a lot of different things. If a function is 1-to-1, then each x and y happens only one time. It says time, I swear. It happens only one time. If my x can only happen once and my y can only happen once. If it repeats for either one, not a function. Or I'm sorry, not a one-to-one function. If we're one-to-one, then the function will pass the horizontal line test. That's what we just discovered. An inverse relation, and that's what we're talking about today. Today we're talking all about finding inverses. An inverse relation is the set of ordered pairs we get by reversing the coordinates of the original ordered pairs. All right, so I'm going to make this problem easier just so we don't have to write 40 things. I'm just going to cross out the last two. Looking at those functions in between, -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. Is that thing a function? Yeah, none of the x is repeated. Is it one-to-one? Yes, none of the y is repeated. If it is a one-to-one function, then we can find its inverse. Okay, so to find its inverse here, all we're going to do is take these ordered pairs and we're going to flip them. So -2, -8 becomes -8, -2. -1, -1 becomes -1, -1. 0, 0, 1, 1, 8, 2. That is the inverse relation here. All we had to do was take the x and the y's and we flipped them. That's it. In inverse relation, we use the symbol f to the -1 power to denote the inverse f. Again, you have to be a one-to-one function in order to have an inverse. You have to be one-to-one, otherwise you can't have an inverse. Okay, just a warning here. This right here means inverse. This right here means the reciprocal. They are not the same. Okay, so inverse and reciprocal are not the same. Raising it to the -1 power and f to the -1 are not the same thing. They're similar. They share some qualities, but they're not the same. All right, let's graph it. So this orange line right here, is that a function? Is it one-to-one? Then we can find its inverse. If those two things are true, it passes the vertical line test, it passes the horizontal line test. I gave you the ordered pairs, -5, -2. We're going to find the inverse of -5, -2. What would the inverse of that be? -2, -5. With your neighbor, find the 5 inverse ordered pairs and then graph them. See what it looks like. Go. We take my 5 ordered pairs, we flip them, nothing fancy about them. We graph them, then we connect the dots. My picture is going to look like that. Does my new graph pass the vertical line test? Yeah, that's why the original graph has to pass the horizontal line test. See how it's kind of been flipped vertically and horizontally? That's why it has to pass the horizontal line test, because the new inverse also has to be a function. Okay, that's why it needs to be one-to-one. So yeah, we're good there. They don't have x-axis symmetry or y-axis symmetry, but they do kind of look related, right? A little bit. And we'll look at that again. Here we go. Let's go to this next one. And it brought me great sadness first period when we tried to graph this. Show me with your arm. What is this shape going to be? All right, we're 1 for 1. It's a square root. Okay, good. We got that part. Show me with your arm. What is that negative sign going to do to my graph? Oh, yeah, no one's going to do it. It goes that way. Remember, a negative sign in front of your x, it's going to take your graph and flip you this way. So normally it looks like that. Now it's going to do that. Point for me. Point for me. Which direction is the +5 going to take your graph? Oh, I'm glad every single person is pointing to the right. Why is it pointing to the right? Because that negative. Remember, we can factor that out. So we're right 5. I got one we can all get. Point. Which direction does the -2 take you? Victory. Down 2. We got that one. We were 0 for 7, but we got that one. Right 5, down 2. There's my starting dot. It's a teapot graph. It's opening to the left, so the pattern is 1, 3, 5. I'm up 1 over 1. Up 1 over 3. Up 1 over 5. 1, 2, 3, 4, 5. Make the graph. Find those ordered pairs, find the inverse ordered pairs, and then graph the inverse for me. Go. All right, here we go. We graph it. It gives me that shape right there, that red line and the blue line. We got the two things. Does that graph look like it has some type of symmetry? A little bit. In fact, it looks hopefully like the same symmetry the first graph has, because anytime we graph inverses, they're going to look like this. Show me with your hands, how would you fold your paper so that the two graphs were to match up? Like diagonal. Everybody agree with me? Diagonal. So if we were to take this graph and fold it over this line right there, we would agree they match up on both sides. Same thing on this one. If I were to fold over this line right here, what is that line that I'm drawing on your paper, or that you could draw on your paper right there? Y equals X. And understand why that's going to be the line. How did we find the inverse? What did we do with the ordered pairs? We flipped them. We made the Y equal to our X. We took the X and made it our Y. That's exactly what we did. We took the X and Y and we flipped them. That is why we get this shape when we make our pictures. Okay? Inverses. They have to be 1-to-1. They are X. You just take the X and Y and you flip them, and they're symmetrical over the line Y equals X. If we're given two functions, we can ensure that they're inverses by doing a function composition. So this is why we learned function composition yesterday. F of g of x. If I were to do that and they're inverses of each other, I'm going to be left with x. And also if we did the other way, g of f of x, we would just get x. So let's do that. On this first problem, I gave you f, and I gave you a supposed inverse, f to the negative 1. So I'm saying the inverse of f is that other equation. We are trying to decide, are they inverses or not? And the way we're going to do that is we are going to find f of this inverse guy of x. And if I do this and I get just x in the end, then I know they're inverses. Okay, so let's do it. The inside function is this inverse. So I'm going to take this thing right here, and I am going to substitute it in to that guy right there. So on the outside, I'm getting 2 plus 3. On the inside, I'm plugging 1/2 x minus 3. Okay, we are going to multiply. 2 times 1/2. Those two things are going to cancel. I get x minus 3 plus 3. What happens if I take negative 3 plus 3? They cancel, so what am I left with? X. Oh, yay, I'm left with x. I did the composition and I got x. If I just got x, that means the two functions are inverses of each other. Okay, try the other way. Find the inverse of f of x and see what you get here. You should get x. Try it. This time we're substituting in the other way. So we're starting with this 1/2 x minus 3. And I'm starting with this 2x plus 3, and I'm substituting it in for x. So I'm getting 1/2 parentheses minus 3. And all I'm doing is plugging in 2x plus 3 right here. The 3 and the minus 3 cancel. So I'm left with 1/2 times 2x. Oh yeah, the 1/2 and the 2 cancel. I'm given just x. Since those two things are true, these are inverses. It is just saying, yep, it is a true statement. F of g of x, g of f of x, we get inverses. Here is a picture of those two shapes when I graph them. 2x plus 3, it's the red line. There's the blue line. If I were to also graph the line y equals x, you would agree that I could fold over top of that line and they would be inverses of each other. Questions on something on the front side? We don't need to try it again, do we? Flip it over. Front side, we did it graphically. Back side, we're doing it algebraically. Okay. The trickiest thing about the back side is the domain and range. Okay. The actual finding it, easy. 2 steps to find an inverse algebraically. We're going to do this all the time from here on in your math career. Okay. To find an inverse algebraically. Step 1, just like the front side, we are going to flip x and y. In our equation, we're going to take the letters x and y and we're going to flip their spots. Step 2, to find an inverse, we are going to solve for y. We're going to flip x and y, and we're going to solve for y. Let's do that. Okay, so number one. First thing we're going to do is flip x and y. I don't even see a y. How can I flip x and y? F of x is y. Okay, so I'm going to flip x equals 2y plus 3. I didn't move a number. I didn't move constants. I didn't move exponents. All I did was take the letter x and the letter y and switch them. Then I'm going to solve for y. You guys know how to do that. I'm going to subtract 3. I'm going to divide by 2. Boom. There is my answer. Y equals x minus 3 all over 2. Or you could make that different. I don't know if it's better. 1/2 x minus 3 halves. They're both the same thing. We flipped x and y. We solved for y. That's it. Okay. What's my domain gonna? What is the shape of this original graph? A line. What's the domain gonna be? All real numbers. So is the range. Okay. If it's a line, the domain and range are all real numbers. What about this new shape? What is this new shape gonna be? A line. Domain is all real numbers. Range is all real numbers. Not very exciting. Okay, but we can do it. Questions on number one? Let's do number two. Number two, 5 over x minus 2. 5 over x minus 2. We're going to find the inverse. So if I'm finding the inverse, I'm going to flip x and y first. Then I want to get y by itself. I'm solving for y. What do I need to do at this point to get y by itself? Yeah, we want to get rid of that y minus 2 on bottom. So the way we're going to do that is we're going to multiply both sides by y minus 2. Okay, so over here, that's going to cancel. I get y minus 2 times x is all equal to 5. I'm still trying to get y by itself. So what do I need to do next in order to get y by itself? Divide by x. Divide by x. Divide by x. That's going to go away. Y minus 2 equals 5 over x. So to finish that thing, I'm going to add 2. 5 over x plus 2. That is my inverse function. Let's talk a second about domain and range. So again, we flipped x and y, we solved for y. There's nothing that you guys can't handle with that. Let's talk about domain and range. On this original function, the domain is going to be all real numbers, but x cannot be what number on that original function? 2, because if it is 2, I'd get 0 on bottom back. The range is going to be all real numbers, but y does not equal what number? 0. Why did my y value never equal 0 for this original rational? You can't make 5 0. The top is always going to be 5. There is a horizontal asymptote at 0. 5 on top is never going to get me 0, so I'm never going to get a y value of 0. There's a horizontal asymptote at 0. I'm not going to cross it. So my domain is everything but 2. My range is everything but 0. Now let's look at this inverse function. Okay, so now we're doing this part. We're looking at this guy. My domain, all real numbers. But my x cannot be 0. Because if I had 0 in here for x, that'd be bad. My range is all real numbers. But y cannot be 2. Y cannot be 2. What is the horizontal asymptote going to be on this guy? 5 over x. What can I not get for my y value? That's 0. I can't get 0 because there's a horizontal asymptote at 0. But I'm also adding 2 to that, so I really can't get 2 because I can't get 0 plus 2, so I cannot get 2. There's a horizontal asymptote at 2. Look at what happened. If you are doing it correctly, the domain and the range is going to flip because we flipped the x and the y. If you flip the x and the y, it's going to flip your domain and range. Be able to go back and forth between those two. Trying to make sense on that one. I'm going to skip 3. Let's go to 4. Number 4, a little bit challenging. We're finding the inverse. To find the inverse, I flip x and y. So it's going to be x is equal to 2y plus 1 over y minus 1. Put a star by this one. This is one that we struggle with a little bit. This is a skill you need in calculus. We do this one in calculus, my calculus class, in like a week and a half. Okay, trying to get y by itself. Thoughts on what I do first? Yep, multiply by y minus 1. We get that y minus 1 out of the denominator because I don't like it down there. Okay. Now what? What happens if I divide? Last time we just divided by x. Does dividing by x help me here? No, because if I divide by x, then I get 2y plus 1 over x, and it's still the same. So that doesn't help me. So watch what I'm going to do here. I'm going to distribute this y, and a little bit of just trial and error here. Like, I don't want to divide by x because that would be weird. I'm going to distribute that y here, and I'm going to get this. Xy minus x is equal to 2y plus 1. Doesn't look like it helps us, and it really doesn't yet. I need to keep solving here. So I'm going to move the y's to the same side and everything that doesn't have a y to the other side. So I'm going to get xy minus 2y. So I moved this over and moved this over here. Is equal to x plus 1. So I got my y's on the same side now at least. What can I do now to try to get my y's by themselves? Kara? This is being added and subtracted. I think you're on the right path there. Careful what we're doing. Lydia? Like undistribute them. Good. We're going to factor out the y's. Good. We are factoring out the y's. Both of these things have a y. So we are going to factor a y out. If I factor a y out, what am I going to be left with? X minus 2 is equal to x plus 1. By factoring them out, now it's y times something. And now I can get y by itself. How do I get y by itself now? Divide by x minus 2. Good. Divide by x minus 2. Divide by x minus 2. So my final answer is y is equal to x plus 1 over x minus 2. A little bit tricky there. You got to realize that multiplying or dividing by x didn't help me. So I had to multiply to try to simplify. Let's do domain and range real quick. Domain. All real numbers. X cannot be what for this original function? X cannot be 1. My range is going to be all real numbers, but my y cannot be. Where do I have a horizontal asymptote on this guy? 2. And sometimes you can cross them. We're not crossing them in these rationals. Okay, when they're just degree of 1 on top and bottom, you're not going to cross those horizontal asymptotes. Then we're doing the inverse function. So we're dealing with this guy right here. Domain is going to be all real numbers, but x cannot be 2. We already know the answer. It's just going to be the flip of whatever we found at the beginning. And all real numbers, but y cannot be 1 because there's a horizontal asymptote at 1 because the degrees are the same. The leading coefficient is 1. That's where my horizontal asymptote is. Okay, there.